This is the next video in the chapter on stoichiometry of chemical reactions. Now that we know all about what the different parts of a chemical reactions are, we are going to balance them. So I've pre-written this because this is from one of our very first lectures of this class, so you can write it down if you like. But remember when we talked about Dalton's atomic theory at the very beginning of our Harry Potter and the theory of atoms? And the last part of Dalton's theory said that atoms are not created or destroyed during a chemical reaction, rather they are just rearranged. And they're rearranged to yield new compounds with new properties. So here's an example of one of those. The total number of red atoms and the total number of blue atoms is the same on both sides. So part of that promise to not create or destroy matter is relevant now that we are trying to balance chemical equations. We have to make sure we do not magically create any atoms on either side that weren't there to begin with. So chemical equations must be balanced, meaning they have the same number of each atom on both sides. So same number of every type of atom on both sides. Here that's like having 2 red atoms on each side and 2 blue atoms on each side. So the way we're going to balance the equation is by adjusting the coefficients. Those big numbers that are in front of each of the compounds in the equation. They're just ratios, so we can change those numbers until we find the correct ratio. So we are going to change the coefficient and not, promise me you will not change the subscript. So if we have something like this, 6H2O is part of your equation. This big 6 in the front, this is the stoichiometric coefficient. This is the part we're going to change when we're balancing the equation. We are absolutely never, ever going to change the little numbers, the subscripts, because if we change the subscript, we have fundamentally changed the compound. H2O and H3O or H1O, those are fundamentally different compounds, and we've completely changed the reaction. By changing the number in the front, we are just changing how many waters, 6 water molecules or 5 water molecules or 4. That's just part of the ratio. So remember to always only change those big numbers in the front. So we're going to do a couple of examples of how to practice, but before we do, let me give you a strategy to use for solving these equations, because they can get a bit tricky as we add more and more compounds, and more types of elements. So here's my strategy for balancing an equation. When you start and you're choosing an element to start with, choose an element that is in only one compound per side. And do all of those first. So some sort of a compound that's in just one reactant molecule and one product molecule. And I'm going to draw a line because those are not connected. So start with those compounds and finish with any elemental compounds that you may have. Save those for last. Those are the ones with only one element. So if there's a compound with only one element, do that element last. And if there's compounds with only one elements that are in only one compound per side, do those first. Otherwise, this is a guess and check method. You do it by inspection. You try and figure out how you can change those big stoichiometric numbers to give you the same number of atoms on both sides. Once you are happy with the coefficients you have inserted, you check your coefficients to see if you can simplify them to make sure they are not fractions and to make sure they are the lowest whole number combination you can do. And then you can go ahead and add in the physical states if they're not already included for you. And this may be confusing when you're first starting out, because you may not know whether a particular unfamiliar compound will be a solid, a liquid, or a gas at room temperature. So one good rule of thumb, if you have to make a guess, is to look at whether the compound is an ionic compound or a covalent compound. Ionic compounds, as we know, are usually brittle, and they're traditionally solids at room temperature because they have very high melting points. Covalent compounds usually have much lower melting points, so they are usually gases at room temperature. Again, this is just an approximation. It won't work all of the time, but if you have no idea what to do and you've never seen the compound before, this is a good way to guess. So now we're going to do a couple of examples. I've pre-written them, so pause the video here and get them written down. Oh, I haven't pre-written them. Okay, well, I'm going to write them then, and see if you can pause the video and solve them for yourself before watching me do them. All right, here we go. Balance the following equation. We've got platinum chloride going to form platinum metal and chloride gas. So we need to figure out how many platinums there are and how many chlorines there are and make sure there are the same number on both sides. So if you like to do a little bit of bookkeeping, or this is the first time you've seen this before, you may want to try making a table. You make one row for each element, and you make one column for reactants and one for products, like that. And you can remake it a couple of times to help you count how many atoms are on both sides. So it works like this. We have one platinum on the reactant side. We have one platinum on the product side, so that element is balanced. We have 4 chlorines on the reactant side. We only have 2 chlorines on the product side, so that element is not balanced yet and needs to be adjusted. So this is a pretty simple problem. We have 4 chlorines and 2 chlorines, so we just need to put a 2 coefficient in front of the diatomic chlorine molecule on the product side, because 2 times 2 will be 4. So we can even make our table again to check that we finished correctly. So we still have 1 platinum and 1 platinum. Now we have 4 chlorines on the left, and 2 times 2 is 4 chlorines on the right. That is our first example. Now let's move on to something a little bit more difficult, where the phases are not included and there's a few more molecules to deal with. So balance this equation with phases. NH3 and oxygen diatomic react to form molecular nitrogen and water. So first, let's check what our current status is. So the elements we have to work with are nitrogen, hydrogen, and oxygen. On the left side, we've got 1 nitrogen, and on the right, we have 2. On the left side, we have 3 hydrogens, and on the right, we have 2. And on the left side, we have 2 oxygens, and on the right, we have 1. So none of these elements are balanced. We have our work cut out for us. So according to our rules, we usually try and find any elemental compounds like this diatomic oxygen or diatomic nitrogen, and we leave those for last, because compounds with only 1 element are easiest to finish with. And we try and find compounds that, we try and find elements that are in only 1 compound per side to start with. So nitrogen is in only 1 compound per side, hydrogen is in 1 compound per side, oxygen is in 1 compound per side. So we can start anywhere we like in this case. So I'm going to say, let's go ahead and start with nitrogen, just because it's on the left. So there's 1 nitrogen here, there's 2 nitrogens there. So let's try putting a 2 in front of the NH3. We now have 2 times 3 is 6 hydrogens, and there's 2 hydrogens on this side. So we can multiply this molecule by 3, because the least common multiple of 2 and 3 is 6. 3 times 2 is 6 hydrogens. 2 times 3 is 6 hydrogens on that side. And that just leaves us with our oxygen. So we have 3 times 1 is 3 oxygens on the product side and 2 oxygen on the reactant side. Now this one is a little bit trickier. You can't multiply 2 by an integer to end up with 3, but you can multiply it by a fraction, which is a legal move, even if it is a little uncomfortable. So if your algebra is a little weak, you can write it all the way out. So this compound has 2 oxygens in it. I need to multiply it by some coefficient x to end up with 3 oxygens like the product side has. And so if we solve for x, x is going to equal 3/2, or 3/2. So 3/2 is going to be our coefficient for oxygen. As uncomfortable as it makes you feel, we can use that as an intermediate coefficient until we finish simplification. So let's check our elements again to make sure we're balanced. So nitrogen's 2 times 1 is 2 on the reactant side. There's no coefficient here. We can just write a 1 if we want. 1 times 2 is 2 on the product side. For hydrogens, we have 2 times 3 is 6, and 3 times 2 is 6. So those are both good. And for oxygen, we have 3/2 times 2 is 3, and 3 times 1 is 3. So those are balanced now. But remember, in our steps, we said that we need to simplify this equation so that we don't have any fractions as coefficients before we are finished balancing the reaction. So the easiest way to remove the fraction is to multiply by the least common denominator. And the least common denominator of these numbers is 2. 3/2 is the only number with a denominator. So we'll go ahead and write the equation again and add in our new twice as large coefficients. I like to write the molecules involved in the reaction and the arrows and the plus signs in one color, like pen, so I remember not to change them. And then I like to write the coefficients and anything that I added in a different color, like pencil, to remind me that that's the part that I put in myself. So we've got 2 times 2 is 4 in front of the NH3. 3/2 times 2 is going to be 3 in front of molecular oxygen. 1 times 2 is 2 in front of molecular nitrogen, and 3 times 2 is 6 in front of the water. So there's my coefficients. The only thing left to add now is the phases. NH3 is a compound that you may not have seen before, but as we talked about in our instructions, we can make a guess based on whether this is an ionic or a molecular, ionic or covalent compound. So nitrogen is a non-metal, as is hydrogen. So this is going to be a covalent compound, and we guess that covalent compounds are usually gases. Oxygen is a non-metal diatomic, which is a gas. Nitrogen is also a non-metal diatomic, which is a gas. And water usually exists as a liquid, unless it's at a particularly high temperature. So there is our complete balanced reactions, coefficients and with phases. All right, so now let's move on to our trickiest one yet. We don't even have the equation to start with. We have to work out of a word problem form. So this one says, write a balanced equation for the reaction of magnesium nitride and water to form magnesium hydroxide and ammonia. So we're looking for these clue words in the problem. So to form, that's going to be sort of our indication of where the reaction arrow is. So everything that reacts to form are going to be the reactants. And everything that is formed, those are going to be the products. There are clues in the sentence that will help you look at how to set up the equation. So we know that these two compounds will go on the left and these two on the right, but now we need to remember our rules for writing ionic and covalent compounds from the nomenclature to get those written. So magnesium nitride is going to be magnesium, which usually takes a charge of +2 because it's an alkali earth metal, and nitride is for nitrogen. Nitrogen usually takes a charge of -3 from the nitrogen group, and that means this is going to be an ionic compound because we have a metal, non-metal. So we can just swap the charges to become the subscripts of the other compound, which gives us Mg3N2 as our formula for magnesium nitride. And again, we're writing this part in pen because this is definite and isn't going to change when we balance the equation. So our other reactant is water. Water is often the solvent for a reaction, but it can also be a reactant. We have this word clue to form. That means we write the arrow here. It might also say something like yields or produces will indicate you need an arrow. Magnesium hydroxide is our next compound, And one clue is that all of the elements that were in the first side will also be on the second side for a balanced equation. So you'll need to have magnesium, nitrogen, hydrogen, and oxygen on both reactant and product side. So magnesium usually has a charge of +3, and hydroxide is one of our polyatomic anions, which has a charge of -1. And again, this is going to be a metal and a polyatomic, so this is going to be an ionic compound. So we can just swap those charges for the opposite subscripts. That puts a 1 below the magnesium, which we can leave out, and a 3 next to the OH. But remember, we can't just write the 3 next to it because that makes it look like there's only 3 hydrogens. We want to indicate there are 3 hydroxides, so we have to put parentheses around the hydroxide piece to give us magnesium hydroxide. And the last compound is ammonia, which we actually used in the previous problem. Ammonia is the common name for NH3. All right, arguably the hardest part we have now completed. Let's move on to our real task, which is balancing the equation. And let's try it without the table this time to see if we can handle it. So I don't see any compounds that have only one element in them to save for last. And I see that magnesium is in only one compound per side. Nitrogen is in one compound per side. Hydrogen is in 2 compounds on the product side, so we'll save that one for last. And oxygen is in 1 compound per side. So we'll just save hydrogen for last, and we'll move left to right for no other good reason. So magnesium, there's 3 on the reactant side and 1 on the product side. So I'll add a 3 in front of magnesium hydroxide. We can do nitrogen next. There's 2 nitrogens on the left. There's 1 nitrogen on the right. So we'll add a 2 in front of ammonia to make 2 nitrogens. We'll save hydrogen for last. There's 1 oxygen on the left side. And this computation of oxygens is going to be a little bit tricky. So in the hydroxide component, there is 1 oxygen. There are 3 hydroxide components in magnesium hydroxide. And there are 3 magnesiums, and while we're here, I've just noticed that I put the wrong charge for magnesium, so let's pull over and fix that. Magnesium should be a +2 charge, because that's what we did on this side. Magnesium should be +2. This subscript should be 2 for magnesium hydroxide. Okay, how much damage did we cause? I think we only need to change this number. There we are. So we've got the coefficient of 3 times the number of oxygens in 1 hydroxide, which is 1, times this coefficient for hydroxide, which is now 2. 3 times 1 times 2 is 6. So there are 6 oxygens on the left side and 1 oxygen, 6 oxygens on the right side and 1 on the left. And so we can put a 6 in front of H2O to make this 6 oxygens on both sides. Okay. Hopefully still readable. The last element is hydrogen. So there are 6 times 2 is 12 hydrogens on our left side. We have hydrogen in both of the compounds over here. So again, we're using one of the polyatomics. So we have 3 molecules times 1 hydrogen per polyatomic times 2 polyatomics. 3 times 1 times 2 is 6 hydrogens. Plus over in the ammonia, we have 2 times 3 is 6 hydrogens there. So we should have 12 hydrogens on both sides, 6 oxygens on both sides, 3 magnesiums, 2 nitrogens. Okay, exhausting. Let's double check and see if there's anything we need to simplify. Our coefficients are 1, 6, 3, and 2. So that is the lowest we can make the ratio of those. So we don't need to do any simplification. We don't have any fraction. The last thing we need to do is add the phases. So we can predict the phases using our knowledge of covalent and ionic bonds. So this was an ionic compound. We can predict that ionic compounds exist as solids. Water exists as a liquid. Again, magnesium hydroxide is an ionic compound, so that's going to be a solid. And ammonia we used in the previous problem, and we labeled it as a gas because that is a covalent compound. So there, amidst all of that mess, we have our balanced equation. 1 magnesium nitride solid plus 6 water as a liquid produces 3 magnesium hydroxide solid and 2 ammonia gas. Okay, so now we can balance equations. We have one more special type of equation to balance, which is an all ionic equation, and we will do that one in the next video.